Okay. Um, actually, our next topic is basically, or the next lesson is basically the compositions and like using the compositions. Yeah, that's our basically main topic. But just wanted to show you one last figure regarding the topic that we covered previously, and um, and there is it's not so much important, but just a few comments on the figure that's given in the in this PowerPoint regarding the when we are comparing the relative oil volumes from a CC experiment versus CVD or DLE. So this figure is showing you if you have a CC experiment and if you have a CVD experiment, if you have relative oil volume, which is the oil relative volume to dew point volume. Okay, so this is again important that this VRO is equal to VO over VS. If you have this kind of relative oil volume from CC and CVD data, and if you plot that data, what you will find out, again, the first thing that you will find out that this until a particular pressure, like which is the first depletion pressure below PSAT in CVD, so this would be like first pressure less than PS in CVD. So until that pressure, the CC and CVD VRO, they will be identical. Okay, and then as we move forward, as we deplete below, further below this pressure P star, uh, so this guy is our P star. If we further deplete below this P star value, what you will find out that the CVD VRO will always be less than the corresponding CCE VRO. And the reason is mentioned here in this figure is from the SP monograph. And the reason is that in the CVD VRO, the reason why it's lower is because we in a CVD experiment we are removing the equilibrium gas phase, right? When we are removing the equilibrium gas phase, this the C7 plus, the total C7 plus content in the CVD gases, we are losing it because we are producing this equilibrium gases. So that's why the remaining gas that's in the PVT cell, it becomes leaner, and then it has less C7 plus content, and it has the tendency to drop out liquid less compared to what we have in the CCE experiment. Okay, and at low pressures they start crossing because in the CCE experiment we have a stronger revaporization because we have a lot of gas there, and since there is a lot of gas, then the gas starts revaporizing the oil, so the oil starts to shrink more in the CCE experiment at low pressure compared to the CVD where we have less gas. So that's why in the CCE experiment at low pressures, the relative oil volume starts to drop sharply compared to what we see in the CVD experiment. Okay, so that's just a general figure when we are comparing the VRO volumes and the VRO data from the CCE and CVD tests, especially for gas condensate reservoirs. Okay, so that was just a few comments on this figure. Now we jump to our topic, which is compositions, like how you quality check the compositional data. And compositional data, we believe that's the most important data in any PVT report um, because like if you have a PVT report, generally you would like to use it, for example, for US model development. And when you do US calculations for all the different experiments you have in the PVT in a PVT report, there is one thing that's common that is affecting all the PVT calculation, and that's the composition you are inputting in your PVT package. Okay, so it's very important that we QC the compositions and see if and try to find out if there are any inconsistencies in the lab procedures or if there are uncertainties in the measurement. So that's the goal there, and that will help us finding out whether like how much we should trust the lab reported composition, and how much room should be there in adjusting the composition when we are tuning the EOS model. And that's something we always do, like when we develop equation of state models. We always consider some uncertainty in the lab reported composition within the measurement errors and try to modify it such that it brings consistency in all the calculations. Okay, so starting this topic, when we talk about the compositions, the types of QC that we generally do is one is this recombination QC, and the other one is the mass to mole conversion. Okay, so these are two basic QCs that can be very easily done in any PVT report, and should always be done to check for the consistency. But again, there is one thing that's very important to know, that these two QCs, recombination QC, um, so what I'm writing here is that recombination QC and mass to mole conversion QC uh, are only relevant to QC the lab calculated data for compositions. Okay, and the best example to explain this is the DLE material balance QC. Okay, and the DLE density QC, or the separator density QC, where we know that the lab, the reported compositions or the reported densities by the lab for the DLE and separator test, those are calculated values from the material balance. Okay, and when we are doing the QC, we are again applying the material balance and see if the calculated values exactly match the lab value, and that's just again to check whether the lab has applied the same procedure, or if they have actually measured those compositions. Yeah, yeah. So the same idea is applied here. And Matthias, he went through this topic in detail in this lesson of Matthias' lecture on getting familiar with lab compositions, right? So he did a lecture, a very detailed lecture on getting familiar with with the lab reported composition, and there he mentioned that when the lab reports compositional data, there are some measured values, and then there are a bunch of calculated values. Okay, so this QC, the recombination QC, and this other QC, which is mass to mole conversion QC, that is just to check whether the calculated data is consistent with the calculations that should have been done in the PVT lab, like with all the procedures that should have been used in the PVT in the PVT lab. Okay, so that's just checking whether the calculated values are calculated in a way that are calculated in a way that uh, that's usually used by the PVT lab. Okay, and in this QC, what we are trying to do is in the recombination QC, the first thing that we do is we calculate this the gas weight fraction, right? So this gas weight fraction, and from the reported density, the gas molecular weight, average gas molecular weight, and the reported GOR. And then we can also calculate it from the lab reported compositions. Okay, so this would be like what the lab has used, and this would be like a calculated value for us. And then we just compare that this value here on the left, the FGW calculated from this information, GOR, gas molecular weight, oil density, is it the same as the FGW that we have calculated on the right from the reported composition? And also, most importantly, that's this FGW, because here we are using the mass fraction of a component, right? Component, so that's a component I. So we have a bunch of components, C1, C2, C3. We calculate this for all the components, and it has to be the same for all components, and it should be the same as FGW calculated from this API, GOR, and gas molecular weight. The same thing we can do for the on a molar basis. So this is the FG value on a molar basis using the density, oil molecular weight, and GOR again, and then can do the same for each individual component and compare the two values, and they have to be exactly the same. Okay. And again, this is something also Matthias discussed. And whatever we are discussing here, that's already been covered in this Matthias lecture on getting familiar with lab compositions. So this FG value here, you can see that we have an average molecular weight of the oil. So PVT labs, they generally measure oil molecular weight, but in most like occasionally, usually the PVT labs, they when they calculate this FG value, uh, the oil molecular weight they generally use here in this equation is a calculated value. And that's something also Matthias mentioned in the lecture. And we can just do a very small recap of what he covered in the lecture and what we are discussing on this slide. And again, here is you can see that, like for example, for flashed oils and yeah, for flashed oils mainly, PVT labs they should have measured an average molecular weight and an average density or gravity. But they also report like they also report a calculated value for the molecular weight and density. So sometimes PVT lab they report both the measured and calculated molecular weight. And sometimes they only report a calculated molecular weight value. And for the density, generally they always report a measured density. And they sometimes also report a calculated density for the flash oil. And the way the calculations of the density and molecular weights are done are using these equations here. The average molecular weight, simply the using the mass fractions of each component, and the lab reported molecular weights, which are kind of, again, these can be very arbitrary. Okay. And this equation here, this is again, this is based on ideal volume mixing. Okay, what do we mean by ideal volume mixing is that if you take, for example, 1 barrel of gasoline and 1 barrel of kerosene, and if you mix them together, you get 2 barrels of the mixture. Okay, so that's what ideal volume mixing is, and that's the basis of this equation. And generally, ideal volume mixing is accurate for flash oil, where you don't have these lighter components like C2, C3, C4 a lot. So there the ideal volume mixing can generally work. But again, when they are calculating these densities, they are assuming some arbitrary set of specific gravities for individual components, which may or may not be accurate for the given field. Okay, so that's why it's always, if the lab has reported a measured density and a measured molecular weight, we can always do the calculation of the molecular weight and compare the values. Okay, and they may or may not be the same. Like the for molecular weights, the calculated and measured values can be as different as maybe like 20, 10, 20 units. But if you have large differences, that doesn't necessarily tell you that the measured value is wrong. Because again, when you are doing the calculation of the molecular weight and the density, you are assuming some set of arbitrary density and molecular weight values. Okay, and those may or may not be representative of your field. And in general, if you have a measured density, uh, generally the density should be very, very accurate, within 1.5%, for example. Okay, and then on the next slide we have uh, this mass to mole conversion. So and that's something also Matthias discussed, that the lab, they measure the mass fractions, especially for flashed oils, and then they calculate the mole fractions based on the component molecular weight and the average molecular weight, which we have already discussed how you can calculate that value. And then you can always compare the calculated value with the lab reported value, which should be exactly identical if the lab has used the same procedure. Okay, so let's just do a small recap of what Matthias went through in his lecture. So this is the PVT report, or the data from the oil PVT report, where we have a flash gas composition and a flash liquid composition and a reservoir fluid. And Matthias went through in detail what is the flash gas and flash oil. If you have a bottom hole sample or MDT sample, you have a pressurized fluid. The PVT lab, they have to first flash that liquid at some conditions, standard condition or ambient lab conditions, to get the two products, the gas and oil, and they measure the compositions of those products through gas chromatography. And for the flash liquids, they generally measure the mass fractions. For flash gas, they can either measure mole fractions or mass fractions, but here, like, we are assuming, okay, they have measured the mass fraction, for example. So so these two columns that are highlight, like they are, which are highlighted, or the text with orange, uh, column D and column G, those are the only measured compositional data. Okay, the PVT labs, they also measure, for example, the GOR, the density. In terms of compositions, when you look at in the compositional tables and the lab provided, these are usually the measured compositions. And then the mass composition of the flash liquid and the flash gas. And then the PVT labs, they provide you the composition in mole percent here. So this is what the lab has provided in terms of mole percent. And here what we try to do is we try to calculate the composition in terms of mole fraction by ourselves, and see if the calculated value matches the lab value. And it's here on this slide, mass to mole conversion, mole fraction calculated from the mass fraction, and you require an average molecular weight value, right? So we have to calculate this average molecular weight first here for the gas and for the oil, using the equations that are given in the slide, and also here, this equation here, for the molecular weight. So for the flash gas, there is the calculated molecular weight is generally very accurate, because there is very, very little uncertainty in the molecular weights of the heavier fractions, and generally we assume that the compositions are measured accurately. So the gas molecular weight calculated from this equation, it should be should be an okay number. And then these mole percent calculated compositions, they are also kind of, they should also be kind of okay. So for flash gas, it doesn't really matter what the lab is measuring, whether mass or moles, because we know that the conversion should be accurate. Uh, for flash liquids, the mass fractions are reported or measured, and then you can calculate these mole percentage. So this is the lab measured data. This is this should have been calculated from the mass fraction by the lab. These are calculated values. And again, if you want to calculate mole percent from the mass percent, you need the average molecular weight. And so one way of getting the average molecular weight is to use this formula here again, and this would be a calculated value. Okay. And for the flash liquids, as we have discussed already, that the PVT labs, they should provide you, they should have measured a value for the flash liquid, even though they may not provide you that value, but you can always ask the lab to give you that number, and you can see here that's the measured value, 251. Okay, and the calculated value is 253, not big difference, like plus minus 2%, but this can go as high as 10 or 20 units on a molecular weight level. So here what Matthias tried to do is to calculate both and calculate the mole percent both using the calculated molecular weight and an average molecular weight, and you see they are very close, not big difference, because the calculated and the measured molecular weight, they were pretty close. And again, you can compare these calculated values with the lab data, and they should be similar. Okay, and okay, now when it comes to reservoir fluid composition that we are generally very interested in, so the interesting thing that people are not generally aware of is that the reservoir fluid composition is never generally measured directly. Okay, so the things that we measure are its products, and then we calculate a reservoir fluid composition, whether it's a bottom hole sample or a surface sample, any sample. The reservoir fluid composition is always calculated from its products. And again, the way PVT labs they calculate the composition is this weight percent is calculated from the, to calculate the weight percent composition, you need a gas weight fraction, FGW, which we also try to discuss, and this recombination gives us this FGW, knowing the density of the flashed oil, the gas molecular weight, and the GOR, which we also have in the report. Which we have in the report here. The GOR we have, and the density of the flash oil, which should have been measured. Yeah, so for flash oil, the density should always be measured by the lab. And so once you calculate this FGW value, you can calculate this total composition, knowing this weight percentage from the flash gas and the flash liquid. Okay, and then that's just a simple equation again here given. Yeah, if you just rearrange this equation, you can get the equation to calculate Wi, and I guess it's here, which Matthias has mentioned. Wi equal to Woi times 1 minus FGW plus WGI times FGW. Okay, so that you can calculate here and compare it against the lab data. And that those should be spot on. And then you can convert this calculated mass fractions to mole fractions using again this equation, and there you need yeah, so there can be two ways of calculating this mole percentage of the reservoir fluid. One is first calculating this Fg value on a molar basis, which is using the density again, the molecular weight, and the GOR. And but here the molecular weight is of the flashed oil. Okay, so you can calculate this Fg value using the oil molecular weight, and generally PVT labs they use the calculated molecular weight in this equation, and that's kind of the reason why I have this comment here, that what MO value PVT lab has used in the calculation of FG, right? So that's something you can check, but you can calculate FG value from the calculated molecular weight or the measured molecular weight, and calculate the composition in mole percent and compare it against the lab. The other way of doing it can be that you first calculate the average molecular weight of the reservoir fluid, again the same way as we have done here, using this formula here, because we have the composition on a mass basis and we have the individual component molecular weight. So you calculate an average molecular weight of the total fluid and then apply this equation here uh, to convert to the mass basis, to convert to mole percentage. So if you are interested, we can just do that exercise very quickly. I can say MRO, that's the molecular weight of the reservoir oil. Just subscript. Okay, and then what we can try to do is try to apply the same formula here. Just adjust it accordingly. So it has to be the mass of this and the molecular weight of, okay, so 157.71 gram per gram mole. And then what you can also check is that this number is similar to what we have here. Okay, this is the molecular weight of the reservoir fluid, like at the bubble point, and this is what we have calculated from the compositional data. Okay, so they are similar. But this molecular weight here, it's calculated from the material balance using the average measured molecular weight, and this one is calculated from the compositional data and the assumed component molecular weights. Generally, PVT labs, they don't provide you this number, which is calculated from the material balance, but they should always provide you, they generally always provide you this number, which is the molecular weight of the reservoir oil from this compositional data. Okay, and then we can calculate this so we can calculate this mole percent using this other method, which is Wi times the average molecular weight of 4 divided by the individual component molecular weight, which is here. Okay, and then just drag it down, and what you will see okay, so if you compare these three numbers, they are kind of identical. Okay, so that's another way you can calculate the molar composition from the lab reported mass fractions. Okay, and then again, these are the gas weight fraction and the gas mole fraction, calculated from the GOR density molecular weights. And you can also calculate these FGW and FG values from the lab reported compositions and what we have discussed, and try to mentioned it in the presentation, that these on a mass basis and also on a molar basis, the two numbers should be identical and should be the same for all components. Okay, so what you see here, this FGW is almost identical. It's like kind of identical for all components. FG is also identical for all components, and this number here is same as this number, and this number here is the same as this number. So yeah, so this is kind of doing what the lab like is this is kind of doing the QC of all the lab reported calculated data. Again, I'm emphasizing we are not doing any QC on the on this measured data. Okay, these are the measured values of regarding the compositions. So these are the measured values, and whatever QC we are discussing here, recombination QC, mass to mole conversion, we are calculating what the lab has calculated in the PVT lab and have reported in the PVT report. We are calculating the same things from using the same input the lab should have used for their calculation and comparing the results. And both the results, our calculations and the lab calculated data has to be exactly identical if the lab has used the same inputs they are supposed to use for their calculation. Okay, so